Okay, in this video I'm going to continue on with my thermodynamics and statistical mechanics videos. So we've taken quite a detour into mathematics, and it's now time to get back into the thermodynamics itself. So we're on video number 20, and I'm now going to do Einstein Solids number 4. I'm going to talk about the multiplicity of a large Einstein solid. Now in previous videos, namely Einstein Solids 1 to 3, I came up with the multiplicity function for an Einstein solid, which is has an energy of q units of energy, and it has n oscillators. And you'll see later on, or may have seen already, that that's the multiplicity for bosons, but that's just an aside. Now, let's begin. So what we're going to require here is Stirling's approximation and Taylor's series. So that's why you'll see, or that's hopefully why you'll realise that I went into the mathematics, so I wouldn't have to discuss it here. So let's begin. We know that the multiplicity for an Einstein solid is q plus n minus 1 factorial divided by q factorial and then n minus 1 factorial. We know that it has q units of energy, it has n oscillators. Okay, what we're looking to do is come up with a better solution for this, a better way of looking at this. So what we're going to do is we're going to take the natural logarithm of it. Now, you may or may not realize that in actual fact the natural logarithm of the multiplicity is in actual fact the entropy. But look, we'll leave that alone for the moment. So let's take the natural logarithm of both sides to come up with a more comprehensive, or not comprehensive, a more usable formula. So the natural logarithm of the multiplicity is going to be the natural logarithm of this function here. But we know the rules of logarithms. Log a over b is log a minus b. So we're going to get the natural logarithm of q plus n minus 1 factorial minus the natural logarithm of q factorial and minus the natural logarithm of n minus 1 factorial, like that. Okay, that should be pretty straightforward to you. Now, taking the natural logarithm of a factorial is involving Stirling's approximation. So we can now rewrite, I'm going to use a different pen, we can rewrite the natural logarithm. So just to remind us what Stirling's approximation says, it says that if you take the natural logarithm of n factorial, what you'll get is n log n minus n. Alright, that's what Stirling's approximation says. So let's just apply it here and try and be as careful as we possibly can be. So natural logarithm of the multiplicity is going to be equal to q plus n log I need to do one more thing before I carry on. I need to make an approximation. See this 1 here. This factor of 1 is very small, so I'm going to get rid of that, and this factor of 1 here is very small in comparison with n and q. So really what we're going to do is do that and do that. Okay, now we're good to go. Sorry, I omitted that. So the natural logarithm of the multiplicity is going to be equal to q plus n log q plus n minus q plus n. That's the first one. Next we're going to have minus q log q plus q. And finally we're going to have minus n log n plus n. Alright, so we can see that we can make a small bit of cancellation with these additional factors here. They can go like that. Okay, because that's just the way the signs are. Now what we're left with is that we have q plus n, we have the natural logarithm of q plus n, and we can take away q log q and n log n. What do we do here? Well, we need to make it's a bit of trickery, a mathematical trickery. Let's just look at this term log q plus n. So the natural logarithm of q plus n, and we'll see this trick a few times, so it's best to be paying attention here, is going to be equal to the natural logarithm, and we take out q, and what we're left with is 1 plus n over q. like that. Or we're left with the natural logarithm of q plus the natural logarithm of n, or 1 plus n over q. Okay, by the rules of logarithms. Now, if you looked at my videos on Taylor series, we take a Taylor expansion on this. So we take Taylor expansion of 1 plus x is approximately x. As the Taylor series says. So I'm going to replace the natural logarithm of 1 plus n over q with simply n over q. Alright, and I did that quite comprehensively, I think, in my Taylor series. So now we're left with this. So we can plug all of this in up here instead. Alright, so let's go ahead and do that. So if we do that, we're going to get the natural logarithm of the multiplicity is equal to, and I'm going to switch to green, I think. We're going to get q plus n outside of natural logarithm of q plus n over q minus q log q minus n log n. Alright, pretty straightforward stuff. But if you look at that, we can rewrite it as follows. Q plus n. Sorry, what am I doing? Q plus n. No, I'm going to multiply n. I'm going to multiply this q plus n in. And what we're going to get is q log q. We're going to get n log q. We're going to get n. And we're going to get n squared over q minus q log q minus n log n. So if you look closely, we can see we can do a small bit of cancellation with this q log q and this q log q, simplifying it a small bit, leaving n plus n squared over q plus n log q minus n log n. Alright? So n squared over q is approximately 0. It's very small. Because the numbers here, they're quite close to each other. So that's very small in comparison with these massive numbers of n, n log q, and n log n. They are very big numbers in comparison to this number, which should be quite small. Because there should be a hell of a lot more energy than there is oscillators. So what I can do is I can get rid of this term. So I suppose this is just going into the mathematics of large numbers. So we're left with that the natural logarithm of the multiplicity is equal to n plus n log q over n, because of course I just took the two of these together, like that. Now, we're trying to get a formula for the multiplicity, so what do you think we do? Well, we exponentiate both sides, of course. We do the exact opposite to what we did a moment ago. We know that exponentials and natural logarithms are inverse functions, just giving us our natural logarithm, or giving us our multiplicity. So, we get the multiplicity as e to the n times e to the n log q over n. Okay, if you know your rules of logarithms, you can bring this guy up here as a power. And if you do that, you have, once again, inverse functions here, which just cancel. So I'm going to rub out those and leave q over n to the power of n. Like that. Okay, and we can clean it up and make it look really good by saying e q over n to the n. So the multiplicity of an Einstein solid with n oscillators and q units of energy is e, the number e, q over n to the power of n. Full stop. Okay, I know that looked quite painful, but yeah, we can see that we're after getting quite a simple formula from this formula involving factorials. Okay, so in the next video I'm going to actually use that formula to start looking at the multiplicity function and see how sharp the peak is. So, thanks for watching. Please pass it on to your friends, subscribe to my channel, and if you're in a good mood, you might also click on an ad. Thank you.